Oh,
Hey, Eduardo, how are you?
very good. Thanks
Good.
for listening.
So I've started streaming online. I'm going to share my screen, which has the cover slide on it, and then we'll get going in about 5 minutes.
Great, thank you.
Yeah.
You are live, Nick.
Yeah. Well, good evening, Corvallis and Willamette Valley, wherever you are listening to this final STEAM lecture from tonight. My name is Nick Houtman. I'm a member of the board of directors of Da Vinci Days here in Corvallis, and it's my pleasure to host this final talk tonight, which will bring us in a full circle from some of the topics that we've been talking about for the last 5 weeks. As you may know, Da Vinci Days has been celebrating the creative energy of the Corvallis community for more than 30 years. And in this year of the pandemic, we've moved all of our festivities online and into neighborhoods. Last month, families were joining us with the Kids Kinetic Challenge, decorating their bikes, doing figure eights and other challenges at home, sharing their videos with us. This month, we're inviting the families to join a creative placemaking project, the Sidewalk Chalk Art Challenge. So look at the Da Vinci Days website, davincidays.org, O-R-G, and check out the details about the Sidewalk Chalk Art Challenge. If you or your family, your kids are interested in painting up with chalk, painting up your sidewalks and sharing your videos and pictures with us, we'd love to see what you're doing. It's a great way to connect with your neighbors and with the community, of course. And just as a caveat, we're not advocating that people go do chalk art on other people's private property. So be aware that we want to make sure we're being respectful of where we do that work. But it'll be a lot of fun. We're also planning a series of online concerts that'll be getting going in the next week or so. So keep an eye out for that. We've got some great talent lined up for us, some familiar names in the Corvallis community. And that's going to be on Tuesday nights for the next few weeks. So again, check out davincidays.org or the Da Vinci Days Facebook page, which presumably you're already on because you're watching this broadcast on the Facebook page. See what's coming up. A few thank yous are in order before we get going tonight. I want to call out our sponsors who have stepped up this year to make Da Vinci Days free and accessible to the public and to help us out with all of our expenses. And they include the City of Corvallis, Benton County, HP, and Corvus. So thank them for us. Host a glass, clap if you like, but we really appreciate their support for us. And we appreciate the support we've gotten from other members of the public who have donated to Da Vinci Days over this past few months. I'd like to also thank our producer who has been helping us behind the scenes, Ben Potter. Sadly, I know you'll all be sad to hear this. Ben is away tonight sailing on Lake Tahoe in California. So I know it's a struggle. Somebody has to do it. But I hope Ben's got fair winds and great sailing up there in the mountains. And I'd like to thank our executive director, Carol Hobrock, who is monitoring the questions and comments on Facebook tonight. He'll be sharing those questions with me later during the question and answer period after our talk. As you may know, the STEAM series is all about creativity in science, technology, engineering, art, and math, thus the acronym STEAM. Our theme this year is Ignite. We've been talking about fire, no surprise, but also about augmented reality and art, and about music and math. Tonight, we're going to take a look at a critical technology for the future, specifically the electric grid and renewable sources of renewable energy and how well those two areas complement each other. Eduardo Cotilla Sanchez an assistant professor in the Energy Systems Research Group of the Oregon State University College of Engineering. He'll be talking about his research. He's also has a lab at the Wallace Energy Systems and Renewables facility on campus, which got its start about 15 or so years ago in the wave energy field. Wallace being named for Alan Wallace, who was one of the visionary engineers working on wave energy at that time. The vision for Eduardo's lab is to make electricity infrastructure sustainable for the planet and safe for all people. And they study things like cascading outages in power grids. They study smart grids and microgrids. They study energy access and inclusion, power system protection, resilience, cybersecurity. Just a few of the things that we all depend on, perhaps behind the scenes, things that modern life as we know it needs to function. Eduardo serves as the vice chair of the working group on cascading failures for the Institute of Electrical and Electronics, also known as the IEEE. And with that, Eduardo, please take it away from here.
Well, thank you very much for the introduction. I'm truly honored to be here with our Corvallis community and beyond. And I'm also very happy to be covering the technology aspect of this STEAM series by talking about a little bit about the electrical grid, which we need to be connected right now, doing things like virtual lectures, and it's a very complex issue how to bring resources that we can convert into electricity. So hopefully, the conversation today will capture a little bit of what the grid would look like in a few years, and how we can keep it safe and accessible for everyone. So I'm bringing a few topics and examples of work in my lab, and also some recent work by other folks in the community that hopefully invites us and instigates some Q&A later in the next session. So before I get into more of the contents, I wanted to have a couple of small disclaimers. If you hear some barking background, this is my roommate, Tony Rex. So he will react to anything that's not in the limits of barking. So that's one thing that you might hear. And then the other thing that I wanted to do was to kind of provide some remarks and as a form of an outline for our talk today. And I wanted to show a map of what the electricity grid looks like in terms of a region here in North America. A lot of the work that we do and the examples that I use are based in the US, but they also apply to other continental or national grids. If we consider the full power grid is the largest machine ever created by humans. In the case of the North American grid, you can see here they are essentially divided into three main areas. Here, the Western Interconnection, the Eastern Interconnection, and Quebec, and then Texas Interconnection. So that means that things and like frequencies are synchronized between within one of these areas. So a machine rotating here in Vancouver, BC, essentially it's interconnected in terms of frequency and keeping those angles with the machine all the way down here in San Diego. So if we go to Texas, for example, we can do power transfer, but they might have a different angle, different frequency. So they are still interconnected, but truly one of these areas, it behaves like a unique machine. So one aspect here is that we have essentially different ways to measure how reliable our system is. So there's a lot of examples of regulations and standards that we'll see a little bit later that come from the government, and it will be FERC and then NERC, which is the independent organization that checks that things are working properly and reliably. So that's most of the aspects that I work on. They are in power system reliability, resilience, and protection. So very shortly, reliability is that we expect to have power to connect to a lecture like this. Resilience is that we expect to recover from when we have a big event happening, for example, lightning or an earthquake. And then protection, which is the science, the technology, and also in art sometimes, of how do we design our equipment and our infrastructure so that they can contribute to that reliability and to that resilience. So that's the area that I spend most of my time thinking about. There's also a lot of power and energy that revolves around the market. So that's another subfield of power and energy. And I teach another of my classes is an introduction to power system analysis here at OSU. So we see the physics of how power flows and how you can buy and sell power. And there's many other folks out there that they are experts in power system economics and the different energy markets. So you can see here that in the map for the United States, different areas, we have different markets for energy, and they don't necessarily overlap with the divisions that we have for reliability. So we have, for example, PJM originally comes from Pennsylvania, Jersey, Maryland is one of the largest utilities. California ISO, Independent System Operator, New York ISO, ISO New England. So sometimes they overlap, sometimes they do not overlap. And there's a lot of aspects to consider and in the economics and markets that I will not get into much detail today. You will see a lot of articles out there when we talk about renewable energy and the grid that talks about comparing the prices of electricity, levelized cost of energy, and a lot of different metrics. Today, we're going to be thinking a little bit beyond that to some other problems that arise from, like I mentioned, reliability, resilience, and protection. And then the other aspect that I'm very passionate about, which is energy access and energy justice. So trying to combine that aspect of environmental justice, how it applies to our power system, the delivery of safe electricity for all humans, and how do we combine that with new renewable sources. For example, in our lab, we work with marine energy, wave energy in the case of the coast of Oregon. So I want to, and that essentially covers or needs to cover a lot of the different aspects of the grid. At the end of the day, we only have one infrastructure, we have one power grid. So it needs to satisfy all of these aspects and try to consider them simultaneously and not just problems that they are completely unrelated. So that was kind of the introduction to say that I want to make that connection that sometimes it seems very far of what are the issues about protecting and having a system that is reliable and resilient for the future, while we're keeping in mind a lot of the issues in energy access and justice. So that's serves as a little bit of the outline for today. So this is I'm building a class that I want to offer hopefully next year in energy access, and I was doing my literature review and some of the papers that I will be assigning to students, and there's some recent work that it's starting to connect some of the dots. This is an example. Energy decisions reframed as justice and ethical concerns. This paper was published in Nature Energy in 2016. And I thought this figure was very striking as it compares essentially the consumption of energy per year. So it will be 40 terawatt hours per year between, which is the same amount for the less than 20 million residents that we have in the state of New York, and the 791 million people that live in sub-Saharan Africa minus South Africa. 791 million people, they essentially use the same amount of energy than for per year than the state of New York. So so there's definitely a disparity in access and consumption per capita, right? Not just having the access. So we have 1 billion people in remote communities without accessing to electricity right now. So this is something that I will loop after. If you see this little dot here, the exclusion from subtracting South Africa. This is the country of Lesotho, and this is the location of a project that I will show at the end of this talk as we are connecting the dots on that issue. So I'll go back to Lesotho in a little bit. I also enjoy reading the explanation of how do we even start dealing about energy decisions and what perspective can we have. So I think most of the literature agrees in having the basic elements of cosmopolitan justice as a good starting point that I hope that folks will agree on before I start thinking about energy. So arguments for individualism, where human beings are the ultimate concern beyond any nation states boundaries or different communities. Universality, so that justice concern applied to everyone equally, regardless of their gender or social status. Responsibility, mutual benefit to treat others as they themselves will wish to be treated, and identity, where we need to recognize that we are a member of a global community of human beings, even though we have different perspectives. So that's kind of like the starting point. If we kept going back, we could talk about philosophy, right? But this is the starting point on many of the energy community on how do we start dealing with some of the issues. And then these are kind of like 5 examples that we can have in mind as we're gonna get a little bit more technical later, but so that we can go back and think about what are the examples of energy problems that could be reframed as justice concerns as they are in the literature. So some of the examples are resettlement is a violation of procedural justice. In the recent history, we have 80 million people displaced from their territories after building 300 very large dams. Fossil fuel pollution is a human rights concern. Energy poverty is essentially a violation of distributive justice. What do we do with nuclear waste? Instead of having a challenge for perhaps different locations, now we are kind of like moving that challenge to future generation, right? It's not a location issue, is a generational issue that we need to think about. And then climate change as a common responsibility for all humans. So these are some of the examples that I wanted to bring up as we are getting a little bit more technical with some of the topics that we'll see in a little bit. This other work also does a good job of reviewing some examples of energy justice issue. They provide an example of recognition justice with the Isle of Lewis example in Scotland, where there's been a long process to be able to install wind turbines where they didn't have all the input from the community at the beginning, and then they kept iterating on those plans. And in these little dots here, where they represent the proposal for wind turbines, they finally refine some of the regions where the community in Lewis were not essentially in agreement with where the infrastructure will be located. So so something as relatively simple as a location sometimes it's just violating that aspect of justice. A different source I was reading today, a similar issue that's happening in Norway with some of the communities and the Sami community, where some of the locations for wind plants will disrupt the migration of the reindeer. So again, similar problem where they need to be at the table and shaping that policy. The other example that I wanted to highlight on how that becomes essentially a violation of procedural justice is this study that was looking at representation in different institutions. So there was a firm that was looking at a survey on different energy companies, their executive boards and teams from Fortune 250. So essentially, the summary of the study said that 84% of those executive team members and boards were white males, in contrast to Black, Hispanic, Asian, or female representations. And these numbers got worse if we looked at smaller companies that make energy decisions. So, so this is something to think about, where it's very hard to solve some of the big problems that we have and complex problems if we don't have the right folks representing the local communities and indigenous, northern communities, sub-Saharan Africa communities, wherever we are, and they are not part of that policy making and technical discussion. So those are some of the things that I hope that we'll keep in context as we're looking at some of the things that we can do technically. So going back to the US, I wanted to show some statistics on the largest blackouts that we have seen since, in the past 50, 60 years. So for example, the 1965 blackout in the Northeast, around 30 million people lost power, and that happened in a collapse time of 13 minutes. That's how we go and essentially look at forensics and see what was the nature of the collapse, if there was a cascading issue, which it was a contributing factor in many of these events that we might see. There was another big event in the West that was in 1996. There was also a very fast collapse of the grid, essentially 36 seconds, where all the different generators and lines were disconnecting. I started looking at this event when I was in grad school. And then some folks might remember the 2003 Northeast North American blackout, where essentially 50 million people lost power between the customers in Ontario and in the Northeast of the US. So that was essentially during this time of the year. It was August 14, 2003, and that was essentially a textbook example of how a combination of initiating events like vegetation management, having a very hot day, folks were using the air conditioning, miscommunication, and several initiating events contributed to such a large cascading outage. So the number of these events is actually increasing over time. And that's one of the reasons that we have this group, like Nick, you were mentioning at the beginning. We have been working for a few years, and this is the website where there's some related presentations that you might be interested in downloading. All the presentations on the past few conferences are public from some of our collaborators. So we have a presentation from industry, like I mentioned, PJM, one of the largest utilities on the East Coast. We had a presentation from some European folks in industry, Pierre, also with the University of Belgium. And then we have also some federal representation with Rui from a national lab. Same with kind of mapping a lot of our members. So a lot of the work that we've been doing on the past few years has been trying to see if we can come up with reducing the barrier to understanding these events and trying to make the response to these events essentially shared by different utilities in different locations, no matter where you are. This is a very boring slide, but I'm trying to make a point that if we just go as a utility and start looking at the different standards that we need to use to run the grid, these are just some of the thousands and thousands of pages on regulations that all the utilities under essentially the domain of NERC here in North America, they need to comply with different things. For example, in physical security, transmission vegetation management, how close can we have our trees to our transmission lines so that they don't cause a fault? Do we need to send a helicopter so that they trim those branches? So in many of these aspects and many of these details, I just highlighted here all of those that essentially were mentioning cascading just on the title of that standard. So several of them, no matter if you're looking at cybersecurity, different disturbance monitoring, a lot of them talk about cascading and try to understand why that happens and essentially avoid cascading. The problem was when we said, well, let's talk to the utilities next and see if the different organizations have a very clear standard of how to improve and look at cascading. So we did a survey through IEEE to 225 institutions, mostly utilities, and asked them if they had a formal definition of how of cascading outage in their institution. So 59% essentially did not have even a definition of what cascading would be. So we can imagine that it would be very hard to avoid that kind of big outages if we don't even have a definition. From those that had a definition, also the reasoning for having that analysis was a little bit heterogeneous. Some of them did it just for compliance, or at least for compliance. Some of them did it for looking at the limits on transactions between different areas for other reasons. Some of them did not know what they were running that analysis. So it's a little bit complicated to solve such a large problem if we don't have an agreement on some of the basic questions that we know have contributed disproportionately to such big disasters. So that's one of the motivations why we keep doing this work. This is a picture from the blackout in 2003 in New York, where that was a lot of the pictures came from the city because it was very dramatic to have just everything shut down in the city that never sleeps. One of the statistical and data points is that the bar in Grand Central Station ran out of alcohol in less than 30 minutes. Besides that, it's one of the examples where there was not big disruption or rioting, like if, for example, happened in the 70s. So that's very hard to predict. So again, just a little sample of things that we look at in terms of initiating failures. And then when we're trying to do things like integrate renewable energy into the grid, we need to be very careful so that we can take that analysis into account when we are looking at reliability. So there is a lot of different things that could cause those failures, like I was mentioning, different conditions in protection devices, voltage collapse from having a lot of air conditioning. This is what happened in 2003. One of the things that happened, stalled motors, different stabilities. This is a lot of the things that I work with my students. And then, of course, some communication and operator maintenance, personal error, and cybersecurity attacks. So a lot of the things that come together and could cause that amount of problems. So one of the things that we looked recently was looking at different frameworks of resilience and how we can make it a little bit more adaptive, that definition of resilience, so that we can incorporate things like renewables, because renewables they change very quickly, right? So we can have wind and we can have solar, and some of the analysis that we have been doing in the past that they were very static, like having a definition for, okay, this portion of the grid is resilience. That doesn't really work anymore because things change very quickly. And if we have a forecast and now August 14 is very, very hot, that means that we are going to have a deficit of reactive power. So something that we've been working on, this is in collaboration with some of our friends in the Idaho National Lab, and my former student, Felicia Cicilio, who's now a faculty member at the University of Alaska, Fairbanks. She just graduated right before the pandemic and moved to Alaska. So she's been the lead on a lot of this work. And just an example of a resilience system, usually we put it on these two axes. So we can see the x-axis will be time. And then we put some sort of resilience indicator here in the y-axis. So this could be seen as damage. So if we are doing right here, we are doing very well. And then phase one, we have some sort of disturbance, and then the system goes and gets damaged until we have the system in a different state. Then we continue, and then maybe we are able to repair, for example, if we have a line, and then the system comes back to an optimum operation point. So if we had a resilient system, what we design is that this first hit, instead of going so deep here upwards, if we have a resilient system, we will go to a lower state of damage. And then we can set up some sort of threshold where we say, well, if we are under this threshold, we are doing okay. The system is still robust. But if we go over that threshold, that's essentially our tolerance, where we might have further damage, or we are not going to be able to incorporate or use more renewable energy because we need to be essentially in safe operation mode. So we've done some work looking at that type of analysis and trying to incorporate essentially an adaptive measure where we might have a resilience threshold that might change according to, for example, the amount of renewable energy that we have in our system. So that's the example that I'm going to show next. Can we have a system where this resilience threshold is going to be adaptive depending on what is the time of the day, what is the seasonality, and how much renewable energy. So that's hopefully one of our contributions to be able to add more and more energy that comes from renewable sources. So this case study that we did in this paper, everything that we've been trying to work on this project, it's been open source. So you can go to this website and download the same data set if you want to play with it. In this case, we got the representation of the Texas system. We call it here a synthetic grid, so that instead of using the actual system that is protected as critical infrastructure, and we don't want to reveal anything that could be used for any sort of attack. There's some research groups that have been very helpful, essentially synthesizing some electrical system that looks very much what the real system in Texas looks like, and it maps things like the distribution of load, the distribution of population, however, it's not one-to-one mapped to the actual system. So essentially, we had used this system with machines to represent the wind turbines that we will have in Texas, and we simulate an event of having a hurricane passing through the coast here in Texas, and trying to see what are the distributions of renewable energy and how much of that energy we can have during that event while having still a resilient system. So I'm not going to go into detail, but this is just a model that we use to represent a DER, which is a distributed energy resource. So this could be, for example, the batteries on your hybrid car, using that resource as essentially a battery for that it's feeding the grid. So it's a generic model, but aggregates a lot of distributed resources that you might have in your system closer to the customer. So we created a few scenarios, and we say, okay, one scenario A would be with no penetration of those distributed energy resources. It could be, again, batteries, vehicles, small PV, small wind. And then we looked at different scenarios, 10% penetration of DER, 20%, 50%, and a random number between 0 and 10%, and up to, again, 50% in different varying scenarios. And then we measure what are the restorative phases with a mean time to recover to come back to some of the states that we were. So that's the type of analysis that we do. And then we look at things like translating that threshold that I showed earlier, and say, okay, imagine that we have, for example, the total amount of load of customers that we have lost for those first few scenarios. If we measure what the disturbance did and what the grid was doing right after that disturbance happened, and then we look at that uncertainty scenario from having renewables, we can go back and translate this. Sorry that it's very small, but this little resilience threshold here, we can have it as a reference and say, okay, if we go over this limit, these scenarios, no matter if we are in this, even in this resilience threshold, there's all the different scenarios are over that resilience threshold. So that's not going to be acceptable for this system. We might have to decrease what is the penetration of DER that we're using at that time. Because in this case, essentially going over 2,000 megawatts loss was not acceptable. So that's how we play between having a threshold that we can tolerate of customers that they're able to recover very quickly versus the variation of different resources. So that's an example of one type of study. Then the second one that I wanted to show is a little bit more connected to electrification of rural areas. So we're going to go back to when I mentioned earlier, we did this work in collaboration with One Power Africa, based in Lesotho, and also a lot of recognition to some of the funding sources, including, for example, the humanitarian engineering program here at Oregon State, and some federal funding. We were able to publish this work last year, and if you find the reference, we also published open source all the different softwares that we use to essentially design a mini grid that we could have in that rural area. The definition of a mini grid or a microgrid is that whenever we are able to have that portion of infrastructure serve a local population, it can be in two different modes. It can be self-sustained, so we're just using whatever local sources we have, but they can also connect to a bulk power system. So a microgrid could be connected to the main grid if it's cheap to bring electricity, and then if there's any sort of issue, for example, a cascading outage, or it's not cheap to bring electricity at that time, then we can disconnect and just make that community survive with local resources. So in this case, the plan to have a mini grid is that they didn't even have access in several portions of the country to the main transmission system that connects to South Africa. So this was mostly for self-sustained operation. And it's very tricky to design because there is a lot of things that one has to take into account. So in this case, we divided the work into two different areas. The first one was more of the, like I mentioned before, a little bit more of the economics of having things running on and off. What is the seasonality of the load profile? When are the different houses in the village using power versus when they are not? And then we run that through an algorithm so that we can get an output that will be essentially that cost of electricity at the end of the day. So this is kind of like what we looked at in one of the villages in Lesotho. The number of houses, what was the peak load? They had a battery. They also had solar and a propane generator, and what was their size. So with that, we could essentially calculate what is the best distribution of resources given any given time of the day. And now the next thing to design this mini grid is where do we put the actual infrastructure? So this was one of the things that was kind of like a newer contribution, because we essentially had to put the low voltage poles, the medium voltage poles, and then the different connections and make a grid that was reliable. So essentially what we worked on, and then Felicia was an excellent lead with this. This is a Google Earth image of the village of Hamakebe. And then there was some exclusion zones that we essentially had to draw on Google Earth, where there are places where you cannot have any type of infrastructure. It could be a hill, or it could be very close to the different houses. So here in the right panel, we have the house location. So we combine in the tool a way to not just look at the actual input and output, but also how do we distribute the actual infrastructure to create that grid in that rural area. And then after that, after we had all of those pole placements in the network layout, that's when we brought the resiliency and the reliability issues. So we were able to tune the algorithm to essentially figure out how much do we want to spend in adding some more reliability or resilience so that they can have the maximum use of the electricity resources. So in this case, if we didn't have any worry about resilience or reliability, kind of the cheapest solution was this configuration with different voltage for the grid, and we were able to provide energy to all. If we started spending a little bit more in that improved reliability, you can see how there's some additions that you might see the difference. For example, here on the left, there was just a loop, but we can add reliability by closing the loop by having two different paths. So if one of those lines was out, we're still able to provide more electricity to other regions. Sometimes in Corvallis, we have suffered a lot of blackouts because we are essentially at the end of the loop in a very rural area. So we don't have the extra paths to add for redundancy. And we can see here in this network, as we add and spend a little bit more money, the algorithm was giving us some more solutions where we essentially have this bigger loop here at higher voltage, and then this other extra loop um, to provide more reliability. So different levels that we can essentially fine tune to make sure that we had a solution that was reliable. And then in this case, this is the cost, the added cost of that added reliability. So in the case of 25% improvement, that extra reliability cost would have been $6,000 roughly. So that would be added to the 20,000 to give 27,000, and you have an intermediate solution here with 25% reliability that includes this large loop, and it worked fairly well for that system. So that's what I wanted to connect back. I think I'm right about the upper limit of the time. So I would like to open it up here with a chance for discussion. This is the last picture that we had near campus before pandemic, and I would be happy to to answer any questions that you might have right now as you're connecting, or maybe later if you think about something. Feel free to send me an email and or check our projects where we have provided those resources from our website, or also Twitter message works very well. So thank you very much.
Thank you, Eduardo. It looks like your lab group is having a very good time. Must have had a good success at some point there to celebrate.
Yeah.
Everybody looks pretty happy.
This was Felicia's graduation, so that was right before she left for Alaska.
Yeah, good one. So we do have some questions that have come in from people watching, one of which connects power outages or the threat of power outages with wildfires, especially in the West. As you know, we've been hearing a lot about wildfires being caused by transmission equipment, especially in California, in the past year or two. Are you or your group, or are you looking at innovations in system development that can minimize outages related to such sparking or such transmission line events at times of high wind, for example?
Yeah, no, this is a really great question, very timely. I was having a conversation with a collaborator today. She's at Miami University in Ohio, and she's an expert in wildfires, and especially in remote regions. So we were looking at that problem, which I haven't been working on before too much, but the reality is that it goes both ways, right? You can have a fire that has already started and having as an initiating failure to the cascading portion. So something like a transformer in a substation, one of the things that we worry about a lot in terms of protection is the temperature. So if you go around campus and or in the Corvallis area and you see the big transformers in the substation, you will see that they have attached very big fans that they seem like kind of rudimentary fans, and some of them are rotating, some of them are not. That's very much measured by the temperature, because depending on how, of course, depending on the cooling, we can add more capacity and we can tolerate a larger current going through. So of course, having a fire that will increase that temperature will be something that it will be really important to, again, be able to change in real time. So to have something like an adaptive setting where the protection mechanism will detect that and then act accordingly, opening and closing some of the circuits. So I think the techniques are very similar to what I've been showing before, but I have not worked with that particular initiating event. So I think that's like one way, one connection, where from fire to failure. And of course, the other one is where some of the failures in the power system, like a transformer blow up, has been the initiating factor in the fire spreading. So kind of like on the other direction. And I think that case has been studied a little bit more and it goes to a lot of the utilities and these standards about doing maintenance and things like I teach a class in the spring that it's smart grid. So we're trying to use more and more sensors so that instead of doing reactive maintenance and fix something when it's broken, the term that we use is just in time maintenance, so that we can have a sensor that will essentially predict that something is going to go wrong. So it's an active area of research. But yeah, very very insightful.
Are those sensors detecting vegetation? Are they weather-based? What sorts of sensing, what are they sensing that would give managers of the system ideas or instructions for what to do?
Yeah, it's a combination of many of those. Some of them are looking at the temperature in different hot spots, so they can see if, for example, the cellulose layers inside the transformers, which is the first thing that can break, is essentially a paper layer. If it breaks, then that means that you're essentially short circuiting that insulation aspect on this, for example, pole mounted transformers that we see, close to the houses. So essentially, it's a lot regarding temperature. There was a study out there, for example, looking at the impact of electric vehicles, because those transformers, the original lifetime that they were expecting to be functional, accounted for having the transformers cool down overnight. And then that cycle, you could find a pattern if you were going to a point where the transformer could fail because it was not cooling down properly. But now over time, we are using electricity, for example, to charge some of the electric vehicles. So we need to be careful that the transformer are getting the right cooling. And there's different algorithms that manufacturers are using so that not everyone starts charging exactly at the same time. There's a little bit of flexibility, and then we can modulate those current spikes so that they don't damage those insulation aspects of the transformer. So yeah, very good point.
Yeah. So those of us with electric cars, my wife and I bought one last year. Should we be charging our car at night, trying to do that as opposed to during the day?
Well, there's it's hard to see depending on how your utility is managing that and how many of them are connected in the whole neighborhood. Probably your car will not be of a huge influence by itself, but in more urban areas where there's a lot of them, for example, I saw studies where some of them were done in Vermont, where I did all my schooling, and there was not a huge issue in Vermont, but the same amount of vehicles and charging patterns in Phoenix, Arizona, will essentially blow up a transformer that had a 35-year timeline in essentially 2 years. So it really depended on the region and how many of those cars will be connecting in different ways. This is
Wow.
something that some of my colleagues did. So I don't remember all the details, but it's something, again, that connects to how do we design those sensors so that they can predict some of the issues in order to perform maintenance just in time and put some resources into our infrastructure.
Thank you. You talked a lot about energy justice when you began your presentation, and I was wondering if, in your mind, in the work of your colleagues, you see a connection, uh, a correlation in energy justice issues and outages. And the case that comes to mind that might show such a correlation is the damage suffered by Puerto Rico
Mhm.
after the hurricane a few years ago, and they've
Right,
continued to struggle with that.
right. Absolutely. I think that's one of the main issues where things like doing proper maintenance and investments sometimes, of course, minoritized communities and marginalized populations are the last ones to get those upgrades or those type of monitoring. So for example, if you see more affluent areas, a lot of the transmission infrastructure goes underground. So it's very much resilient to some of the winds, and we don't have to do so much vegetation management. The tricky thing is when we need to do a repair in some of the underground cables, then it's expensive to go and access. But if there is money there, then that's one of the first places where it will be upgraded. So yeah, I think it's a difficult it's a very difficult correlation when we look at the numbers, and completely agree. The case of Puerto Rico is I have some collaborators there, and it combines some of the economic aspects with a lot of political aspects, and not having the investments on time.
It seems like it's a social justice, of course, and a health issue, as we know that many people in Puerto Rico suffered greatly by not having access to electricity, and those events really bring out our dependence on these systems. I would like to bring in another kind of cause of outage here. I know that some work has been done at Oregon State by people looking at what are called Carrington events. These large discharges, rarely done over a period of centuries, I think, and decades at least, from the sun that can blast the earth with a heavy dose of solar radiation. The solar wind can be extraordinarily intense. I think there was 1850s, 1860s was last recorded one that burned out telegraph lines and actually started fires. And I'm wondering, and there's been some concern about the vulnerability of our grid to another such event. How vulnerable are we, do you think?
Yeah, this I think I had one line about this, and I just skipped through, went very fast. But I have a funded collaboration by the National Science Foundation with Professor Adam Schultz here, also at OSU, and we were precisely looking at that. There's his group has very good models about essentially what kind of currents could you expect coming to your electrical equipment. So we're trying to essentially couple that model with the power flow models that we have on the electrical side. So some of the effects that, like you mentioned, and some of the studies that have been done so far have been very much forensic. So just to look at an inrush current, geomagnetically induced current to the transformer due to, for example, a solar storm, and but we didn't see the global effect at the same time because we didn't have sensors simultaneously in many locations of the grid. Many of the problems of the grid that seem very trivial in other electrical engineering disciplines is that we cannot have a little multimeter and probe at different locations of the system. They are very much miles apart. So until we got better sensor technology, the one that we are using in this project uses GPS in order to align the measurement. So we can measure something in California and we can measure something in Oregon. And then no matter how much delay we have in bringing it to the server, we can still timestamp it with the GPS, a very accurate signal. And then we can see that sequence of events, and we can see the current that has been interactive from whatever it is, a storm. Very similar physics also with some of potential attacks, right? With some sort of E&M weapons. So very similar physics, but I think again, going back to that issue that we were mentioning earlier, is that things could be very much apart. So it's hard to see just with a forensic, one measurement that it was not well measured, and at the same time, it's very hard to understand what happened and learn from it. So we are trying to put together those two different models so that they talk to each other.
Okay, thank you. I'd like to turn just for a few minutes before we conclude here, we're getting close to the top of the hour, to some of the renewable sources that we have talked about, especially at Oregon State, we have a strong and have had for about 15 years wave energy program. We had a presentation by the director of the Pacific Wave Energy Center last summer. And we understand that wave energy at that time was still not cost competitive with other sources. Is that still the case from your perspective?
Well, that's a very good question. I think like I was mentioning at the beginning of the talk, if we're just looking at one metric, that levelized cost of energy is going on the right trend, and I think it's gonna get very close to other sources. I like to kind of reiterate what I was saying at the beginning, that that's not just the one metric that we need, because in this case, if we have wave energy resources that we are able to incorporate, for example, in that microgrid design that I had here, and you're able to incorporate that resource for times of the day or periods of the year when you really need it, then you're essentially avoiding the cost of a very large outage, right? So you're avoiding that heavy tail on the event. So I think that's the right motivation why I'm very excited to collaborate with PMAC and our wave energy program. And some of the things that we are trying to work on next is precisely that interaction between the price of having that sold to the bulk power system, which is great, and we are very close to be competitive in that sense. But for me, coming from the protection and access domain, I'm not that worried about how many cents per kilowatt hour, more or less. I'm more worried about looking at the whole year and be able to provide a safe and secure operation without spending millions and millions of dollars because we have one of those horrible events. So I'm already saving money in my mind just by having that option. But it's hard to quantify, of course.
Yeah, that's a great perspective that we often look at the bottom line, how many cents per kilowatt hour are we paying for our power? But looking more broadly at the resilience of the system, knowing that we have to avoid, we need to avoid those serious major events, the big disturbances that can send the power out for days or weeks at a time, is also an important factor to keep in mind. Along those lines, as you know, we have an innovative energy producer in company in Corvallis, NewScale Power. And NewScale, I should tell our audience, is in the interest of full disclosure, has been a supporter of Da Vinci Days over the years, and we've appreciated that support, of course. From your perspective, does the kind of small-scale modular power that NewScale is working on play a role in system resilience and avoiding issues with outages?
Yeah, of course. I think when we look at the composition and thinking about the case that I mentioned before of designing a microgrid, right, that it's very flexible. I think power and energy delivery flexibility is going to be increasingly important in that grid of the future. And there's going to be locations where we just don't have the geography or the resources to have offshore wind or to have wave, and it's going to be very important that we have adequately sized resources. For now, that is the best that we can do, and in this case, modular nuclear is going to be a great complement to that portfolio, particularly for that location. So I think in all my work, I'm very agnostic on the type of source that we have. I think we just need to always trying to integrate the best solutions that they are local, so that we don't have a lot of transmission losses and we are not spending money on heating very long transmission lines. And then if we don't have those local resources, find ways in which they are cheap to bring to that location and to serve those customers on a variety of scenarios. So most of the time, the solution is to combine different sources because they all have different degrees of strengths and weaknesses.
Thank you. So if I hear you correctly, having a variety of sources available to fill in, to create the base load, which I know is an issue in managing systems when we don't have, when it's dark out, or when the sun's, when the wind is not blowing,
Right.
so forth, is important for the future. We're at a little after 7 o'clock. We've promised people we'd be done by around 7. So with that, I'd like to thank you again very much for sharing your expertise and your thoughts with us tonight, Dr. Cotilla Sanchez. It's been a pleasure to learn from you, and wish you the best. Again, for our audience, if you want to look at davincidays.org, our website, or the Da Vinci Days Facebook page, you will be you'll check out some of the opportunities to participate in the sidewalk chalk art event coming up, and some of the entertainment projects that we have coming up in the next few weeks. There's some great things happening this summer through Da Vinci Days, all online in this odd pandemic summer that we're experiencing here. And with that, I'd like to thank you all for joining us and wish you the best, and have a good rest of your evening. Thank you again.
Thank you all for connecting. Have a good night.
Thank you. Bye-bye.